In the last part of this chapter, I talk about the exceptions to the octet rule. You remember when we were drawing the Lewis structure of the compounds, I told you that we need to complete the octet on the central atom. It's true for almost all the atoms except some important exceptions. There are 3 types of exceptions. I just talk about 2 of them. Some central atoms are okay with less than 8 electrons. We call them incomplete octet. Like the first 3 elements in group 13 are very famous for that incomplete octet, like boron, aluminum, and gallium. Like for example, if you want to draw BCl3, boron just has 6 electrons or 3 pairs of electrons. Never put 4 pairs of electrons on boron. Another type of exception to the octet, we call it extended or expanded. Atoms like phosphorus, sulfur, iodine, or arsenic are very famous for this type of exception, like SF6. Look at SF6. If you draw it, you will have 6 pairs of electrons or 12 electrons on sulfur, and this molecule is perfectly stable. In the last part of this chapter, I would like to talk about bond energy, because we already talked about the bond and bond length and everything about the bonds. Now let's see what is the energy that we spend for breaking the bonds. The average enthalpy change to break the bonds is called bond energy. How to calculate the bond energy for a reaction? We said it's an enthalpy change, right? Delta H is sum of broken bonds minus sum of the bonds formed. Broken bonds are in the reactant side. Formed bonds are on the product side. So this is for the reactants. And this is for the products, right? So let's make it more clear with an example. We are supposed to estimate enthalpy change for the following reaction. So C2H4 plus Cl2 gives C2H4Cl2. If we draw the Lewis structure, you see the importance of Lewis structure here. If you draw the Lewis structure, C2H4, an organic compound, is, looks like this. Cl2 is a Cl-Cl bond, and C2H4Cl2 is this. So, what's happened? A double bond has broken, a Cl-Cl bond has broken. Instead, a single carbon bond is formed and 2 carbon-chlorine bonds. Be careful, a double bond between the 2 carbons is different from a single bond between the 2 carbons. So, if you want to follow that formula, these bond energies will be given. Bond energies for carbon-carbon single bond, carbon-carbon double bond, carbon-chlorine, and chlorine-chlorine. So let's first determine which bonds are broken. We said carbon-carbon double bond and chlorine-chlorine. So the carbon-carbon double bond and chlorine-chlorine, we put these 2. We put their bond enthalpies, right? And then minus the bonds formed. What are the bonds formed? 1 carbon-chlorine. 1 carbon-carbon and 2 carbon-chlorines. So 1 carbon-carbon, 2 carbon-chlorines. Plug in the bond energies given, and your delta H is going to be minus 158 kilojoules, which shows an exothermic reaction. All right. Well, practice on everything that I talked about, especially the Lewis structures. In the next chapter, we will talk more details about theories of bonding.